Good morning. How are you doing? Good. Today we are going to discuss the circular motion. However, before I start my lesson today, I would like to remind you what we did in our previous classes. So, we studied what we call the linear motion, which is the motion in one dimension. And we also studied Newton's laws, and we applied them to one dimension or to linear motion. And here I would like to remind you of one of the most important laws of nature. This is Newton's second law, the force equal mass times acceleration. Today I am going to introduce you to a new concept that is called the circular motion. And in particular, I would like to discuss these two concepts with you, what we call the centripetal acceleration and the periodic time. However, before I start, let me ask you a question. You all did wash your clothes, right? And you noticed that the washing machines have to go through a spinning cycle. So the machine rotates very, very, very fast. Do you know why the washing machines have to go through this spinning cycle? Any guesses? Okay, if you don't know the answer, okay, I will tell you. Actually, this is very important in order to get rid of the water in your clothes. And how this works, in order to know how this works, you have to study the circular motion. I am not gonna answer this question in this lecture because it's gonna be only 10 minutes lecture. However, the next class I'm gonna explain to you how this works. So, let me start with the concept of circular motion. What really we mean by circular motion? Circular motion is defined as the motion of a particle on a circular path, or just on a circle if you want. So, this is my circle. And let us assume that this is a circle of radius r. And this is my particle. And this particle moves with constant speed along this circle. So this is called uniform circular motion. Okay, let me write it here. Uniform circular motion. This is what we are going to concentrate on today, which means that the motion happens with constant speed. So the speed v is equal to constant. Okay, so now let me ask you a question. If the speed is constant, does it mean that the acceleration vanishes? Does it mean that the acceleration is equal to 0? Any guesses? No, right? Yeah, right. Why? Because, as we discussed previously, that the acceleration actually is a vector quantity, and it is defined as the rate of change of the velocity with respect to time, and actually that both the velocity and the acceleration are vector quantities. So, if the speed is constant, this really doesn't mean that the velocity itself is constant. Why? The velocity is a vector quantity. So let us try to understand how the velocity changes its direction as our particle moves along the circle. So now my particle is here. So where is the direction of the velocity? Right. Exactly, it is tangential to the circle. You see? Because the particle moves in this direction. So at this point, the velocity actually points along the tangential to the circle. Now my particle is moving, and after some time, it will occur here. So now where is the velocity vector? Exactly, again, it is tangential to my circle. So you see, although the speed is constant, the velocity as a vector is not constant. And as you know, that the speed is just the magnitude of the velocity. So when we take the derivative of the velocity as a vector with respect to time, we find that actually that the acceleration is not zero. And I will leave it to you as an exercise to show that actually that the magnitude of this acceleration is equal to v squared over r. All right? I will ask you to do this derivation in a homework problem. And this is called the centripetal acceleration. And this symbol C just denotes it's a centripetal acceleration. Okay, this is the magnitude actually of my acceleration. What about its direction? Centripetal means center-seeking, and in fact, the direction of this acceleration is toward the center. So this is the direction of my acceleration. And again, I will ask you in a homework problem to show that this acceleration is toward the center. And because of that, we call it the centripetal acceleration. Okay? Any questions so far? All right, good. However, we know from Newton's second law that if there is acceleration, there has to be some force that provides this acceleration. So, what kind of force this could be? Well, actually, this depends on the situation. So, we all know that the planets rotate around the sun. And in this case, it is actually the gravitational field that provides the needed force in order to for these planets to continue circling in circular orbits. Okay, here I have a demo, and I would like you to try this yourself. So this is just a ball attached to a string, and now I'm gonna actually rotate this ball so fast. Okay, now my question is, what provides the centripetal acceleration in this case? Right, it is actually the tension of this string. And I want you to take this and try, and you'll find that actually you have to exert some force in order to keep it in a circular orbit. Okay, good. So now let me move on to another concept, which is the periodic time. So what is the periodic time? The periodic time is defined as the time needed for our particle to make one complete cycle around this circle. How we compute it? It is very easy, right? We all know that the relation between time, speed, and distance is that the time is equal to distance over speed. Okay, so what is the distance in this case? Anyone? Yes, exactly. It is the circumference of the circle, which is 2 pi times the radius r. divided by the speed. And we all know that the speed is constant in this case, so it is 2 pi r divided by v. So this is what we call the periodic time. So now let me give you a question. Okay, we know that the Earth circles the Sun. This orbit is not exactly circular, but we will assume for the simplicity that it is circular. So knowing that the distance between the Earth and the Sun, the distance is 150 million kilometers, find the centripetal acceleration that the Earth will experience. Okay, I want you to find the centripetal acceleration. And I would like you to compare it with the acceleration on Earth due to the Earth's own gravity, which is 9.8 meters per second square. I would like you to compare these two numbers to get a rough idea about how this acceleration is small compared to our Earth's gravitational acceleration. Okay, good. Any questions? Perfect. All right, then if there are no questions, thank you, and I will see you next time.